Part 4 of our notes today is all about what's called the factor theorem. The factor theorem states that a polynomial, f of x, has a factor, x minus k, if and only if f of k is equal to 0. Now, if you think back to when we talked about the remainder theorem, when we did division, we said that if we plug a number in, the k, from the factor, whatever we get out when we plug that number in, when we evaluate, is the remainder. So basically, if the remainder is 0 when divided, then the divisor is a factor of the polynomial. So if, when we do synthetic division for these polynomials, these binomials and polynomials, if we get that the remainder is 0, then we can say that that is a factor of the polynomial, or it would divide evenly. That's what factors are. They're evenly divided binomials into larger polynomials. So let me show you an example. First things first, if we were to set up synthetic division to decide whether this binomial x plus 1 is a factor of the polynomial, we would use the k value of -1. Remember, it's the opposite of the binomial for k, for the house number. And we grab all of our coefficients. We have a coefficient of 1 in front of x cubed. We're missing the x squared term. Then we have -13 in front of x and -12 at the end. The steps for synthetic division were bring down and then multiply. -1 times 1 is -1. Then add straight down. 0 plus -1, -1. This should sound familiar because we've done this before. -1 times -1 is +1. Add straight down, we get -12. -1 times -12 is +12. -12 plus 12 is 0. Now remember, when we labeled these for synthetic division, that last term is your remainder. And since we have a remainder of 0 in this problem, that's good. Put a little smiley face right here. This means that x plus 1 is a factor of f of x. That's what we know. If that is any number other than 0, I'd put a frowny face right here and say it is not a factor of f of x. And that's as simple as it is. So the factor theorem allows us just to check quickly if it's worth dividing that polynomial so we can continue to factor the polynomial completely. If we look at example number 10, the k value I'm going to use is 2, because again, it's the opposite of what you see in the binomial, and I see x minus 2, so I use +2 as the house number. The coefficients, 6 is in front of x cubed, then we have 8 in front of x squared, -34 in front of x, and -12 at the end. No missing terms in this one. Big mama. All right, we bring down, we multiply, we add, we multiply, we add, we multiply, we add. And again, in my remainder spot, I have a 0. That's good. We want that to happen. And if our remainder is 0, then we can confidently say that the binomial we divided by is a factor of f of x. Now, I do want to point out to you that if we had a synthetic division problem that ended up with numbers like this underneath, I'm just going to make something up right here. If it was like 1, and then it doesn't really matter, but our last number was like 5, where that means our remainder is 5. Would we say that the binomial we divided by is a factor for the random problem I wrote on the side? No, we would say whatever it is not a factor. Boom. So really, again, the factor theorem allows us to quickly check to see if something is worth dividing by so that we can factor the polynomial into smaller terms, because it has to divide evenly for it to be a factor.